My name is Daniel Tafaradi Baba. I'm from Tennessee Clinical and Translational Science Institute at the University of Tennessee Health Science Center. I'm a PhD in epidemiology. I focus on nutritional epidemiology and chronic health outcomes. Today we'll discuss about the nuts and bolts of logistic regression. So in today's presentation, we'll discuss about logistic regression, what logistic regression stands for. We will describe some assumptions of logistic regression, and we will describe when to use logistic regression as a statistical analysis method. And we will describe the outputs of logistic regression. So logistic regression is a statistical analysis method that's used to examine the association between predictor variables or risk factors and a binary outcome. So binary outcome variables are outcome variables that have two levels. So a yes or no type, or a 0 or 1 type kind of outcome is a binary outcome. Binary stands for 2. So a 0 or a 1 outcome, or a yes or no type outcome, health outcomes are binary outcomes. So the logistic regression is used to analyze the association between predictor variables or a given predictor variable and binary outcomes. The outcome variable for logistic regression analysis has to be either yes or no type or a 0 or 1 type. So example binary outcomes are having heart failure, which means yes, or sometimes it's coded as 1, or no heart failure, which is coded as 0. So in logistic regression, we have a log of the probability of having the health outcome, or y is equal to 1, divided by the probability of y is equal to 0, equals the intercept plus the beta coefficient times the predictor variables. So the logistic regression has these four: the logarithm of natural logarithm of the probability of y equal to 1 or yes, divided by the probability of y equal to 0. That's equal to the intercept, or alpha naught plus the beta i's times the x or predictor variables. So in this formula, the y is the dependent or the outcome variable. The alpha naught is the intercept, where the predictor variables, for example, if we have multiple predictor variables, when the value of the predictor variable is 0 or the reference category, we get the intercept. And sometimes, for example, if we are looking at predictor variables which are continuous, like BMI, blood pressure, cholesterol levels, and the likes, there is no case where we have 0 value, but we can have the reference value. So when we have the reference value for the predictor of interest, we have the intercept. So in logistic regression, and the intercept is not of great interest. Usually we will rely on the beta coefficient or the slope of the variables to calculate the. So the beta here is the coefficient of the i's risk factor. So when we have multiple risk factor or covariates, we have beta coefficient is calculated for each of the covariates in the model. So in logistic regression, we have, like in the previous slide, we looked at the logistic regression had the formula of log of p yi equals 1 divided by the log of p y equals 0. So the p of the probability of y or the outcome being 1 or yes is the probability of the event. And this probability is calculated by taking the exponent of the beta coefficient or the slope of the model divided by 1 plus the exponent of the beta. So this exponent, the exponent that we have here stands for raising a number 2.72 to the beta coefficient. So exponentiating the beta coefficient in epidemiology or biostatistics mean raising the 2.72 to the beta coefficient. So we have 2.72 raised to the beta coefficient gives us the number in the numerator, and then 1 plus the exponent of beta gives us the denominator. And so the quotient, the exponent of beta divided by 1 plus exponent of beta gives us the probability of the event, or the probability that y equals to 1. And the probability that y or the outcome is 0, that means the event didn't happen, is 1 minus the probability that the event happened, because in probability, the probability adds up to 1 or 100%. And so if we find the probabilities that that of the event, and then we can find the probability that the event didn't happen by subtracting the probability that the event happened from 1. So in the previous slide, we said the formula for the logistic regression is the log of the probability of y equals to 1, or the event happening, divided by the probability that the event didn't happen, which equals the log of p divided by 1 minus p, based on the this line and this line. And this equals the intercept plus the beta coefficient times the predictor variables. So here in the parentheses, we have the probability of an event happening divided by the probability that the event didn't happen. And this division is called odds. This is very important. So the division of the probability of an event by the probability of no event is called odds. So in logistic regression, we have the log odds of an event equals the alpha or the intercept plus the beta coefficient of the predictor variables. And as we'll see in the next slides, usually from studies such as case control studies, we see in the literature the measures of association that are reported as low, the odds ratio. The odds ratio means the ratio of the probability of an event to the probability of no event in the exposed group divided by the probability of an event divided by the probability of no event in the non-exposed group. So the odds ratio, the ratio of the odds of an event in those exposed to the odds of no an event in the non-exposed group. So in many statistical analysis methods, there are assumptions that we have to take into consideration to apply the statistical analysis method for the data analysis. In logistic regression analysis, we do not have too many assumptions unlike linear regression and the likes. Some of the assumptions in the logistic regression are the outcome has to be a binary outcome, a yes or no type, or a 1 or 0 type. And the other assumption is that there is a log linear relationship between the outcome variable or the event and the exposure variables. And the other assumption in logistic regression is that there are no influential observations or no extreme outliers. So the influential observations are observations that can affect the beta coefficient significantly. So whether they are in the model or not, this kind of observation can change the beta coefficients, and thus they can change the fitted Y value or the predicted Y value or the classification of the other individuals. So observations with extreme value that change the beta coefficient when included in the analysis are taken as influential observations. When we say observations, they are recorded. So for example, if we take a sample of patients that come to an emergency department or an outpatient department, and say, if you are a physician, you might have like thousands of patients, and then you take a sample of say 50 of those, and take information, collect information on those like age, gender, race, blood pressure, vital signs, and do physical examination and send laboratory examinations, and you collect all those data. So the data for a given patient is considered as like that single patient is considered as an observation. So some of the information that's collected on the patients might be extreme. They might be very far away from the average or the other data points. And so when this kind of extreme data values exist, we have to examine, are they really valid? Are they, is there an error in entering the data? And why is the person or the individual, the participant, very different from other participants? And make sure that the data is valid before we can proceed with data analysis. I hope everybody hears me, right? So the influential observations also change the predicted probability of being an event or not. So to examine the assumptions in logistic regression, we'll use the, we'll look at the log linear association between the log odds of the outcome or the risk of type 2 diabetes. When we say the log odds, we mean the natural logarithmic odds of the outcome, which means logarithm with a base of 2.72 instead of 10. So looking at the association between, linear association between the log odds of the outcome and the predicted variables, here we have the log odds of the outcome plotted on the x-axis and the predicted variables plotted on the y-axis. So looking at the scatter plot between age and the log odds of type 2 diabetes, looks like there is a linear association kind of between the age of the participant and the log odds of the outcome. And looking at body mass index or BMI and the log odds of diabetes, looks like slightly deviated from linear, but not too much. It's not very extreme, so we can still use logistic regression. For insulin and pedigree, there appear to be a log linear relationship between the predictors and the log also of the outcome of type 2 diabetes. So the pedigree is diabetes pedigree function, which provide the synthesis of the diabetes mellitus history and relatives of the participant and genetic relationship of those relatives to the participant. It's a numerical variable. So we will use this data. This data comes from the PIMA Indian diabetes 2 data that's included in ML bench statistical package in R. We'll use this data set and we have renamed the data into diabetes. And we will use another data on fertility for the example in our today's presentation. So in this figure, it's a smooth plot of the predicted logit odds versus the predicted value. The plots are linear for age, insulin, and pedigree, and nearly linear for BMI. So looking at influential observations. So to look at the influential observations in logistic regression as well as linear regression, we use Cook's distance. So the Cook's distance is calculated by omitting a given observation from the analysis and calculating the beta values and predicting the outcome, and then include that same observation in the analysis and calculate the predicted Y or the event, and take the difference between these two predicted Y values divided by the standard deviations of the residuals times the number of parameters to be estimated, and that gives us the Cook's distance. So the Cook's distance tells us whether a given observation has influence, or whether a given observation is an influential observation or not, or whether it significantly affects the beta coefficient that's estimated. So checking influential variables using Cook distance in logistic regression is as important as in the linear regression. Some use a Cook distance of 1 as a cutoff point to say a given observation is an influential observation. Others use 4 divided by the sample size minus the number of parameters to be estimated, including the intercept. In this case, the Cook's distance, looking at the association between BMI, age of the patient, the pedigree function, the blood insulin level, and the risk of diabetes. There is no Cook's distance which is greater than 1, but looking at the latter criteria, 4 divided by the sample size, in our case, after removing those with missing values, we have about a sample size of 393. And the number of coefficients that we estimate for each continuous variable is 1. For BMI, we estimate 1 beta coefficient. For age, we estimate another beta coefficient. For pedigree, we estimate another beta coefficient, 3. And for insulin, we estimate another beta coefficient. So we got 4 beta coefficients plus the intercept. So we estimate 5 beta coefficients. So our parameter is 5. So dividing 4 divided by 393, the number of sample size or the number of observations minus 5 gives us the cutoff point for the Cook's distance. So looking at that, there are quite a few observations that can be taken as influential. especially those with observations with Cook's distance above this horizontal red line, which is at the cutoff point based on the latter criteria, can be taken as influential. So when we do the analysis, we might check whether the values for these observations are valid or not, and might decide to keep in the analysis or remove them and see how they influence the beta coefficient that are estimated. So the logistic regression can be used to examine the association between behavioral risk factors and the risk of coronary heart disease. Examine the association between behavioral risk factors and the risk of type 2 diabetes. Examine the association between behavioral risk factors and the risk of ischemic stroke. And it can be used for examining the association between behavioral risk factors and the risk of opioid overdose. So in all these cases, the outcome can be taken as binary outcome. So the risk of developing coronary artery disease, a yes or no. And we can take smoking as the behavioral risk factor. The risk of developing type 2 diabetes, say based on BMI, based on family history, and many other behavioral risk factors or other risk factors. And the risk of developing ischemic stroke based on nutrients, for example. And so whether the patient develops a stroke or not, it's a yes or no type of outcome. So logistic regression analysis can be used to examine the association between several risk factors and binary outcomes. So the outcomes in the example are yes or no type. So for example, whether a smoking person developed coronary artery disease or not. By exponentiating the beta coefficient, we get the odds ratio. So the odds ratio is the measure of association that is usually reported from methods that use logistic regression for the analysis. And so as the name indicates, in odds ratio, we are dividing one odds to another odds. That gives us odds ratio. And the odds means the probability of an event happening in those exposed divided by the probability that the event did not happen in those with exposure, divided by the probability of the event happening in those not exposed, divided by the probability that it did not happen in those not exposed. That gives us the odds ratio. So we can put this odds ratio in a table like this. So for example, if the outcome is being infected with coronavirus virus, and the probability of the event is yes or no, being infected with coronavirus, and our exposure variable is whether a person constantly used mask or not. So we can take the exposure, a protective exposure in this case, wearing mask, and then if a person constantly wore mask when they went out of home, were they infected during this coronavirus pandemic? If the answer is yes, we have A, and then the absence of infection is B. So the probability of the odds of being infected with coronavirus while using mask is A divided by B. The odds of coronavirus infection in those who use mask is A divided by B. And the odds of coronavirus in those not using mask is C divided by D. And the odds ratio is the division of A over B over C over D, which gives us AD over BC. This is very easy to remember. when you create, this is called a contingency table or a 2x2 table. And if you put the numbers in here as A, B, C, and D, this A, B, C, and D stand for the number of people who are who you constantly used mask but still got infected, and those are who were not infected. And then we have AD over BC, another amino divided by before Christ. You can easily remember with that abbreviation. So if we instead want to calculate the odds of COVID infection in those not wearing masks, then it will be BC over AD. If we instead wanted to calculate the odds of being infected with coronavirus in those not using masks, that means those who did not use a protective, the odds ratio would be calculated by dividing BC over AD. So when we conduct a logistic regression analysis, we have to look at first plot and look at the data. So in these plots, we plotted the BMI. It's a scatter plot of the BMI by the risk of diabetes. The diabetes is either 0 or 1, as you can see here. And we have BMI ranging from around 18 to around 60. So as you see, we have only 2 levels for the diabetes, either 0 or 1. But for BMI, we have a range of values. So since diabetes is a binary outcome, we can use the logistic regression for the analysis. So first look at the data, make sure that there is no linear association. If, for example, diabetes is actually a continuous variable or an ordinal scale variable, logistic regression might not be the appropriate analysis method. Again, look at the diabetes and BMI. Here it looks like there is an association. Those who are positive for diabetes tend to have a higher average BMI. So on the x-axis, we have diabetes who are tested positive and tested negative. On the y-axis, we have a BMI. And here we have the median. We have the median here. And these are the range of the values for BMI. And if we compare these two box plot, those who tested positive for diabetes have higher BMI. So it's worth examining the association between BMI and the risk of diabetes. This is another plot. It's a sigmoid curve, which shows the association between BMI and diabetes is not actually a kind of straight line. It follows some sigmoid kind of curve. So if the association between BMI and type 2 diabetes was linear, we would find, rather than data points concentrated in only two along the y-axis, we might find the values all over the places and might fit a straight line if there was a linear association. But in this case, there is a log linear association, and so we have a sigmoid kind of curve where we have a low on the y-axis, and then as we go across the x-axis, the data points will start to appear. And this vertical line is at a point where at a 50% probability of being having the risk of diabetes, and it can be used for classifying participant into the diabetes or non-diabetes. So in linear regression, we said there should be a linear association between the risk factor and the continuous outcome. In logistic regression, there is a log linear association, which has such a sigmoid curve when we plot the scatter plot between the two variables, the continuous outcome and the binary outcome. The continuous predictor, the continuous predictor and the binary outcome. So in the following R output, the model summary shows the model formula. So when we fit a logistic regression using R, we use the GLM function, and the formula should be specified like this: the outcome variable for the diabetes plus the BMI, the BMI, and we specify the family or the distribution as the binomial distribution. Binomial distribution stands for the binary outcome kind of distribution. It's come from Bernoulli distribution. And the data that's used is diabetes. So I use the data that was generated on Pima Indians living in Arizona to examine the association between BMI, age, triceps, insulin, pedigree function, and the risk of type 2 diabetes. So in this R output, we have the formula at the top. We have deviance residuals, the residual, which means deviation from the event, deviation from the observed and the expected values. We'll not go into detail into this one in this presentation. And then we have the coefficients, a beta estimate for the intercept, which is negative 3.99682. And then we have a standard error for the beta coefficient, the intercept and the beta coefficient is a standard error. And then we have the statistic or the Z value and the probability or the P value, the probability that the calculated Z value is greater than the critical Z value of like 1.96. And then we have the beta coefficient for BMI. We have some information about whether the P value or PR greater than the absolute value of Z is significant or not. So when the P value is 0, we have 3 stars. When the P value is 0.001, we have 2 stars. And when the P value is increases to 0.01, we have only 1 star. And when the P value is less than 0.05 or 0.05, we have 1 period. And when it is greater than 0.05, we don't have the significant levels or legends like here. And this is about another assumption. There is dispersion, or there is a dispersion parameter for binomial family taken to be 1. There are times when we have to use negative binomial instead of the binomial distribution if the dispersion parameter is different from 1. And then we have the null deviance. We don't go into detail into how to calculate the null deviance, but it's a deviance that's calculated when we didn't include the BMI in the model, only when we have the intercept in the model. And then the residual deviance where we have predictor variables like the BMI included in the model. The output gives us some additional information like 11 observations were deleted due to missingness. Because the data had some missing values, about 11 variable observations were deleted from the analysis. And then we have a KK information criteria. This helps us to compare two models to examine whether we specified our model correctly or not. So, and then we have other information about the number of Fisher scoring iterations. This is about model convergence, how long it took for the model to give us to calculate the beta coefficients that are optimum for the model or for the data. So to get the odds ratio, we have to exponentiate the beta for BMI. And I said exponentiate here means taking 2.72 raised to exponentiate to the beta value. So that gives us the odds ratio. So to continue with our evaluation of the logistic regression output, the final table indicates every unit increase in BMI is related to 1.111 times higher odds of being positive for diabetes. And the odds ratio can be reported as OR, which stands for odds ratio, equals 1.11. In the bracket, we have the 95% confidence interval, which ranges between 1.08 and 1.14. And we also have p-value. The p-value tells us whether the odds value, the odds ratio is significantly different from 1. If the odds ratio equals 1, or if the 95% confidence interval includes 1, the p-value usually is greater than 0.05. That means it's not significantly significant. And in this table, we have some other additional information, like the number of observations. This is before missing values are removed from the model. And we have other information like the R-square. This is a pseudo R-score. It doesn't have the same meaning as the R-square in linear regression. In linear regression, the meaning of R-square is the percentage of the variance in the outcome explained by the exposure variable or by the BMI. In logistic regression, the R-square tells us the classifying ability or discriminatory ability of the model, or whether the model can classify a given observation into having diabetes or not, properly classify or not. So whenever the R-square is low, the model probably is poor. So the maximum R-square is 1, and the minimum sometimes is close to 0, like here. So the pseudo R-square tells us how well the predictors predict the outcome. And as the model fits improve, the pseudo R-square increases and is always less than or equal to 1. So if you have any question, please, you can send me a chat. You can speak up, and I'll be glad to address and go forward with the other slides. So once we fit the model, we have to examine whether our model actually fits the data. So we have to conduct some model goodness of fit test. Some of the techniques that we use for logistic regression are like using the Hosmer and Lemshaw goodness of fit test. In Hosmer and Lemshaw goodness of fit test, we have a chi-square that is reported, and the degrees of freedom. This is based on the number of grouping that we use. So what's examined in this, in the Hosmer and Lemshaw goodness of fit test is they compare the predicted and observed data for the diabetes, grouping them into different groups, like 10 groups. In this case, I use 10 groups. And then we have a p-value. And if the p-value is statistically significant or less than 0.05, it means our model is poor. The model doesn't fit the data well. But if the model fits the data well, for example, in our case, the p-value is 0.1049, which is greater than 0.05. So it's a good indication that our model is in the right direction. But if the goodness of fit test p-value is less than 0.05, probably our model is not well specified. So we have to consider other predictor variables and examine again the goodness of fit. And the other is using deviance test. In our case, the p-value based on the deviance test comparing a null model to a model with BMI, we have a p-value of 0.323. Again, the interpretation is in the same way. If the p-value for the model goodness of fit test is significant, that means your model is not well specified or your model is not correct, and you can't use, probably you have to try other covariates. So the tests are about whether the fitted or predicted data are significantly different from the observed data. If the tests are not significant, then the model fits the data well. In the following table, we see the outputs of a logistic regression on the association between previous induced or spontaneous abortions and the risk of infertility. So the outcome in this table is infertility. Whether a woman undergoing and who had previous induced abortion, one or two or more previous induced abortion, or spontaneous abortion, one, two or more, and the risk of infertility. So in this table, we looked at the association between previous induced abortion, the number of previous induced abortion, and the risk of infertility separately for the induced versus the spontaneous. So in the first, so the top part of the table is from one model, and the bottom part is from another model. For examining the association between previous number of previous induced abortion and the risk of infertility, as you see, there is no statistically significant association between previous induced abortion and the risk of infertility. The odds ratio is 1.04. It's not very far away from 1. And the 95% confidence interval ranges between 0.56 and 1.91. And it includes the null odds ratio or the odds ratio of 1. When we say the null odds ratio is 1, we mean the odds amount exposed divided by the odds amount non-exposed is equal. When they are equal, the division is gives us 1. So if 1 is found between the 95% confidence interval, and then our odds ratio is not really significantly different from 1 or the null value, and we have to report that there is no association between having previous one induced abortion. There is no increased risk of infertility. Adjusting for, well, in this case, we didn't adjust for any other variable. And looking at 2 or more previous history of induced abortion and the risk of infertility. Again, the odds ratio looks like it's different from 1, but the 95% confidence interval indicates it includes 1 or the null value for the odds ratio. And the p-value is also greater than 0.05. And so we can say there is an association between in the risk of previous history of 2 or more induced abortion and infertility. This will be changed, as we'll see in the next coming slide, when we adjust other variables, and also when we actually take the way that the study was planned. We'll discuss that. So in this table again, looking at the number of previous spontaneous abortion. So for every 1 previous spontaneous abortion, the risk of infertility is increased by about 3 times. And the 95% confidence interval, as you see here, is significantly different from 1. The 95% confidence interval ranges between 1.68 to 5.88. And this means, for example, if we take 100 different data in about 95% of the time, the odds ratio falls between 1.68 and 5.88. The p-value is also very strongly significant. And for those who had 2 or more previous history of spontaneous abortion, the risk of infertility was increased by about 8 times. Again, the 95% confidence interval is significant. It doesn't include the null odds ratio value of 1 because the range is between 3.67 and 18.63. The p-values also confirms that. So in the first parts of the table, we have the pseudo R squared, which is about 0, which means the model is really very poor. We have to adjust for other variables. As we adjust for additional variables, the predictive capacity of the model improves. And also based on the variable itself. So for example, for spontaneous abortion, we have the pseudo R square of 0.133. So when we use each predictor separately, the model fits the data poorly, and previous induced abortion doesn't seem to relate to the risk of infertility. So when we adjust for each type of previous abortion, 0, 1, 2, or more, the model slightly improves. Like compared to having 0 previous history of induced abortion or history of previous spontaneous abortion, having 1 previous risk of previous history of abortion, induced abortion, or 2 or more previous induced abortion, we can compare the risk to having no previous history of induced abortion. So in this table, we included both a previous history of induced abortion and history of spontaneous and previous spontaneous abortion in the same model. So that means for each of the variable, we adjusted for the other variable. And as you can see, the odds ratio for the induced abortion changes, but it's not yet statistically significant. For those who had 2 or more previous history of induced abortion, the odds ratio increased to about 2.28. But as you can see, it's a kind of borderline. It's not statistically significant. The p-value is also close to 0.05, but yet it's not significant. We will see when we take into account the design, this is going to change. So when we look at the spontaneous abortion, history of previous 1 spontaneous abortion as compared to no previous spontaneous abortion, there is about 3.63 risk of infertility. And that is a statistically significant with the 95% confidence interval ranging for the odds ratio between 1.90 and 7.07. And the p-value is also less than 0.001. For those with two or more spontaneous abortion, the odds ratio is 10.53, and the 95% confidence interval ranges between 4.55 and 25.75. So like, for example, if we go back, the odds ratio increased from 8 to 10 for the spontaneous abortion, for previous two or more spontaneous abortion. Again, looking at the pseudo R-square, we have the R-square increase from 0.133 for only spontaneous abortion to 0.144 when we include both induced abortion and the history of spontaneous abortion, which means that our model kind of improved when we adjusted for induced abortion or spontaneous abortion. So the interpretation is the risk of infertility for those with two or more previous spontaneous abortion is more than 10 times higher than those without the history of previous abortion. And we report the odds ratio like this and 95% confidence interval. Sometimes they report with comma, sometimes they instead use a hyphen or use 2. The 95% confidence interval equals 4.6 to 25.8. It's acceptable, but it depends on the journal that you submit to. Sometimes they specify which one they prefer. Actually, let's have a look at the data on infertility. So this is like the first 3 observations in the infertility data. This is again included in our statistical software for teaching purposes. So the data has education, the level of education, 0 to 5 years, 0 to 5 years, and it goes like that. And then the age of the woman, the participant, and the parity, which means the number of previous pregnancies, the history of, previous history of induced abortion, and whether the patient has infertility or not. 1 stands for infertility and 0 stands for no infertility. And spontaneous, the history of previous spontaneous abortion, 0, 1, or 2. 2 represents 2 or more previous history of abortion. And then we have strata. So the strata is ID, kind of ID. So in this data, what we can see is that actually the study is a case control kind of study, and they match each case to 2 controls. It looks like the data, the first 3 lines indicates that the match arranging by the strata, sorting by the strata. In the original design, they matched a given participant with infertility, who is a case, to 2 controls. And they match them for education. They are in the same range. For age, probably they exactly matched it. They are all 26 years of age, 26 years of age. And the number of previous pregnancies or parity, all have 6 previous pregnancies. So they match the participant, the cases and controls on education, age, and parity. And then, so they have the same kind of ID or strata, 1, 1, 1. When the data, actually the study is designed in such a way, the appropriate or the proper statistical analysis method is conditional logistic regression. It's not the regular logistic regression. In conditional logistic regression analysis, we take into account the matching or the strata. So this is again the analysis taking into account the matching in the design of the case control study. And as you can see, the odds ratio calculated for both induced abortion and spontaneous abortion are really markedly different from the previous one, especially for the induced abortion. In much case control studies, we use conditional logistic regression taking into account the matching. So for the induced abortion, for those having one previous history of induced abortion, there is about 4 times increased risk of infertility, and the 95% confidence interval ranges between 1.61 and 9.9, and the p-value is 0.003. And for those who have 2 or more previous history of induced abortion, the risk of having infertility is about 17 times. So the odds ratio is 16.77, and the 95% confidence interval ranges between 3.97 to 70.84. For those with spontaneous abortion, having 1 previous spontaneous abortion as compared to no previous history of spontaneous abortion, the risk of infertility is 7.72. The 95% confidence interval ranges between 3.18 and 18.75. For those having 2 or more previous spontaneous abortion, the odds ratio actually jumps to around like 50 times. So those who have 2 or more previous spontaneous abortion have about 50 times higher risk of infertility. But as you can see, the 95% confidence interval is really very wide. This is proportional to the sample size. We only had about 248 participants in here in this data. So the sample size is really very small, and the 95% confidence interval is very wide. And as the sample size increases, the 95% confidence interval tends to narrow down, which usually the investigator wants to have. Otherwise, there is always a comment that there is a very wide 95% confidence interval. So if you have any question on what we covered so far, you can stop me at any moment and can ask any question. So once we have done, done logistic regression modeling, we have to examine whether our model actually performs well. So how well a logistic regression model performance can be examined using performance indices such as sensitivity, specificity, accuracy, and the area under the curve on the receiver operating characteristics curve. For our model on infertility, we have accuracy of about 80%, 81%, and a sensitivity of about 0.8 and a specificity of 0.83. This means the model is really very good. As the accuracy goes down, or one of the sensitivity or specificity goes down, the model performance actually is, tells us that it's very good. Then sensitivity is like you have certain cutoff point in the probability to classify a given individual into as having the outcome of interest or not having the outcome of interest based on the predictor variables that were used in the model. For example, for the infertility, we used induced abortion or previous history of spontaneous abortion in the model. So based on whether a person has a given number of previous induced abortion or spontaneous abortion, can we classify the person into having risk of infertility or not? So, so based on that, based on whether our model can properly classify a person based on the predictor variable into the exact outcome using a cutoff on probability in the probability that we mentioned or early, the model performance can be high or low. So the sensitivity and the specificity is also based on that. The sensitivity is the ability to detect a condition in those who have a condition. And the specificity is the ability to say there is no event or a condition when there is no one. And the accuracy is the accuracy to tell correctly those who have a condition and those who do not have the condition divided by the total test that is conducted for the whole model. And the area under the curve tells again whether our model is really accurate. And so it's based on the ROC curve, and we'll see in the next slides. So this is a receiver operating characteristics curve or row curve, and it helps to examine the prediction accuracy of our models. So the area under the curve or AUC is the area between the diagonal, this gray line, and each of the other colored lines in the model curves. So this is for the PIMA Indians data, and the higher the AUC, the area under the curve, the better the model. So for example, when we fit the association between BMI or body mass index in kilogram per meter square in relation to the risk of testing positive for type 2 diabetes. So that is the blue line. This is the row curve for this model. The area under the curve is the area between this diagonal line and the blue curve. And this area, as you can see, is lower at 0.055. And the 95% confidence interval range is between 0.51 and 0.58. This line, the diagonal line, is around 0.5, and the maximum area under the curve is 1. So on the row curve or receiver operating characteristics curve, we have specificity plotted on the x-axis and sensitivity plotted on the y-axis. As we move from the right to left, the area under the curve increases. So for example, if we have a model that has area under the curve here, the area under the curve plot or row plots, the area under the curve increases, which means the sensitivity increases as the specificity also increases, and the false positive decreases. So when we include additional variable for the PIMA Indians data, the area under the curve improves. As you can see here, the area under the curve improves from 0.55 to 0.62. And when we include additional variables like the pedigree function and the blood insulin level, the area under the curve again improves, which means the model, the predictive ability or performance of our model improves. So in addition to binary outcome, logistic regression is also used to model ordinal outcomes and multinomial outcome. In this case, we don't use, so we have to use a different method than the, so using the binomial family distribution, we have to use a different method in R as well as in SAS and many other softwares. But the method is the same, but slightly different. So for ordinal outcomes, the outcomes have more than 2 levels, and there is an inherent rank between the levels. An example is parental education and educational achievement of their children. To examine the association between parental education and the educational achievement of their children, we can use ordinal logistic regression analysis. So the outcome in this case is the educational achievement of their children. The parental education precedes in time the education of the children most of the time. So in this case, we can use parental education to predict the educational achievement of their children. So the educational achievement of the children can be categorized into below high school, graduate education, general education degree, or an associate degree, completion of high school, a college degree, or university or plus. And so in this case, we have multiple levels of the outcome, which is greater than 2. And so to analyze this kind of data, we do not use the ordinary logistic regression, but there is a specific logistic regression analysis for this, for ordinal outcomes. When we say ordinal outcome, it is an outcome with meaningful ranks. So for example, below high school is lower education than the GED. And GED is a lower education than college and the college and university plus. So in such kind of outcomes, we use ordinal logistic regression analysis. Ordinal logistic regression analysis. The term ordinal refers to the inherent ranks between the levels of the outcome variable. We can also use logistic regression to examine the association between predictor variables and multinomial outcomes. In multinomial outcomes, we have more than 2 levels of outcome, and there is no inherent ranking or order in the levels of the outcome. So we can model the association between patient socioeconomic status and their hospital choices using multinomial logistic regression. So a given patient might select one hospital that provides the same service than many other hospitals. Their decision to go to a given hospital can be like the hospital choices are multiple. And so the outcomes are whether they pick one hospital versus the other. And we can model this kind of outcomes using multinomial logistic regression analysis. So these are, they have some kind of inherent features that they share with the ordinary logistic regression, but they are different. So to recap our today's presentation, logistic regression is used to examine the association between predictor variables and binary outcomes, which means outcomes that have 2 levels, a yes or no type, or a 0 or no type. For much case control studies, we have to use conditional logistic regression, taking into account the matching. And of the performance, checking indices, the area under the curve is one of the way to examine logistic regression model accuracy. And for ordinal outcomes, which are the outcomes with inherent ranking with 2 or more levels, we use the ordinal logistic regression. And for outcomes with more than 2 levels that do not have inherent ranking, we have to use multinomial logistic regression analysis. So in all these cases, the outcomes are not continuous variables. The outcomes are kind of whether an event happened or not, and they are kind of count variables. So thank you very much for your attendance. Today's presentation is sponsored by Tennessee Clinical and Translational Science Institute. Our website is located at https://tnctsi.uthsc.edu. My office number is 901-448-1217. Currently, I'm working from home because of the coronavirus pandemic. You can reach me at ddbaba@uthsc.edu. Thank you very much.
All right, thank you, Daniel.